Um, okay, so hi everyone. Thanks very much for joining for the second session today, and for joining for this kind of short tutorial about Pixi. So if you go to the Indigo agenda for today, should maybe make this a little bit bigger. But if you go to the Indigo agenda for today, there's some resources that are linked under my talk. There's if we're this is going to basically be a somewhat short tutorial on the basics of using Pixi for things that you might reasonably want to do in the PyHEP ecosystem. So there's two links here. One is to a website, and so the website is essentially kind of a walk along for the talk. So I would encourage you to basically have this up as kind of a resource as we're going along, and I would encourage you to try and follow along as much as possible. But I'm going to go somewhat quickly given time. There's also a link to the generating repository that has some of the examples that I'm going to be working through today. So you can check that out at your leisure or clone it and follow on as well. Okay, so starting from there, we're going to start off with just kind of an overview real quick. Actually, we're going to get set up before that. So um, I link here some references. This is basically a sub 50-minute tutorial is going to not be able to touch on all the functionality that Pixi has. But I've linked here both documentation from the official Pixi docs as well as some longer multi-day tutorials that I've given in the past, especially around using Pixi for reproducible hardware accelerated environments for machine learning. But if we, on the left-hand side here under the kind of navigator bar, if we go to setup, for people who would like to follow along today, and I'd encourage everyone to do that for the first bit, we're just going to quickly get set up. So my recommendation is that thanks for adding me as co-host. My recommendation is that we're going to minimally want Pixi and Git and also an IDE of your choice. But I'd also recommend that you to try and make what you learned today kind of a shareable resource to also have a GitHub profile or a GitLab profile set up as well. But to start off with, we're going to simply go ahead and install Pixi. And that's super easy to do because Pixi is just a single Rust binary. So in the situation that you're on a Unix machine, that's simply just a curl command. And if you're on Windows, then you can do that with basically the equivalent in PowerShell. So just to show you that also there's nothing super magical about what I'm doing. If we run a Docker container, so if we run Docker run rmti, let's get Ubuntu. So here I'm just gonna install curl real quick, but all we're gonna do is just go back to get this installation command. I'm gonna copy this. Curl should almost be done downloading. And now I'm actually going to edit this because I know something about this container to use bash instead of shell. But we see here that, okay, we've already downloaded and installed the Pixi binary. And it's now telling me that it's also made sure to add information to my local bash RC so that the next time I restart my shell, that everything will work. So that's how easy it is to install. I'm going to also recommend that Pixi also has some shell completions, which are quite nice. So if you click here to follow along with the shell completions, then this basically gives you tab complete. I'm going to copy this, and I'm going to now just echo this contents into the tail bit of the bash RC file. Okay, so if I now look at the tail of bash RC, we now see that Pixi is being added to path and these shell completions are being added. So if I now source my bash RC file again, now I have Pixi on path and it's installed. And I also have the ability to do tab complete with Pixi, which is great. Okay, so we've already got Pixi installed. And I also recommended that you had Git installed on your machine to follow along. In the event that you don't have Git, so if which Git or command-v Git turns up nothing, we can actually use Pixi to install Git. We can do Pixi global install Git, and that will actually install the latest release of Git from Conda Forge in an isolated environment that will still be globally accessible. So I now have Git installed. And from there, I would also recommend if you're not familiar with the Git command line or GitHub to install the GitHub GH utility. But what I recommend is just setting up a repository to follow along for now. You can either do that in the through the GitHub command line, or sorry, the GitHub web interface, or just for today, for time, I'm going to cheat a little bit and use this this kind of scripted example, which is going to create a repository on my GitHub called PyHEP 2025 Pixi tutorial, and then clone it down locally. I'm going to CD into that repository. I have some initial commits there. If you're not doing this from the command line, or if you aren't able to quickly go ahead and do it from the GitHub interface, feel free to also just make a repository, and then you could do a git init in there and get going yourself. But we're going to start off with this repository, and I'm also going to check out a new branch just called feed add example. So we're going to be working on a development branch as we kind of go along for these examples. So now that we've gotten set up, then we can go ahead and do our first kind of example together. Okay, so let me blow this up a little bit. All right, so first of all, we've installed Pixi, but what is Pixi? So Pixi is a modern cross-platform package manager and environment manager that allows us to be able to rather trivially handle very complex environments. And one of the really interesting features is that it will automatically and non-optionally produce a lock file of our environment for us anytime we perform an operation, which means that just by the nature of using it, our environment will be indefinitely reproducible into the future. So this is great because this gives us robust virtual environment management that allows us to now be able to manage conda packages and Python packages and be able to switch between environments really easily. It also allows us to be able to, from a command line, be able to install, update, and remove all these packages, as well as have a full task runner system built right into it, so that if we wanted to, we can create quite custom logical operations or whole workflows inside of our basically environment management tool, which might be handy for doing development. If you're going to try and build something really large, I'd recommend instead using something like a workflow engine like SnakeMake or Common Workflow Language or something like that. But for just having kind of nice one-off tasks that aid in development, I think the task runner system is really great. And some kind of shining features or kind of behaviors that are really great about Pixi is, as I said, it gives us automatic lock files. This is super powerful because this means that any state of a repository, by nature of the fact that it was able to be solved, means that it's reproducible and trivially reproducible into the future. So if this is if a lock file and the environment definition are versioned together in version control, this means that even if you don't touch a repository for 5 years, you can come back and on a totally new machine be able to get the exact same environment byte for byte that you'd had 5 years ago with no additional work. It also means that we can solve environments for other computational platforms than the one we have ourselves. I'm currently running a Linux machine, but I can solve environments for Mac OS or Windows or other other computing architectures of Linux than the one that I have, and vice versa. And Pixi is also the first tool that I know of that has parity of support between conda and Python packages in environments. And what I mean by that is that normally, if you're trying to mix conda and Python packages, you basically install all of your conda packages, and then you just kind of hope for the best and install all of the Python packages on top of it, even if there's conflicts. Pixi is the first tool that I know of that is able to solve the dependencies of conda packages, lock that environment, and then find the missing components that would be necessary for the Python packages and install just those. So this now means that I'm able to use Python packages and conda packages interchangeably in my environments without having to worry about collisions. And then also, it's really fast. Pixi is written in Rust and has a really great resolver. It also has very efficient caching, which means that that takes advantage of a global cache as well as efficient linking of the files into the different environments. There's a blog post that's maybe of interest here all about how that linking is done. But this also means that the first time you install a package is basically, by definition, the slowest it will ever be to install that package on your system. So let's go through kind of a first example of how we would maybe a typical example of things we would want to do with Pixi. Um, so let's go into our example directory. So I'm here now, but then I'll get this out of the way so it's a little bit easier to follow along with me. Um, okay, so the very first thing we want to do is we want to initialize a new Pixi project. We do this at the command line using Pixi init, and we now see that there's a, oh, sorry. So that was fine, but I want to show a different functionality, so I'm gonna remove this pixi.toml real quick. I wanted to do Pixi init example. And so we now see that when I provide a string to Pixi init, that it takes that as a directory path, and it will now create a new directory called example, and there's a file inside of it. So if we change directories into this example directory, and if we look around so if I look at all the files in here, then I see that there's some Git files, some Git attributes and Git ignore. And then I see that there's a pixi.toml. So this pixi.toml is the interesting thing. So to kind of look at this, I'm going to use a utility called bat, which is just a kind of fancier version of the cat utility. If you don't have it, you can do pixi global install bat, B-A-T. And if I look at this pixi.toml, then I see that this is a TOML file. TOML is Tom's obvious markup language. It's a very common markup language that's used for configuration files and many tools. Here we see that inside of this Pixi configuration file, we have a workspace table, a tasks table, and a dependencies table. So we're going to quickly step through what these things are and why they matter. So first of all, looking at the workspace table, we can see that there's an author's channel, name, platforms, and version fields. The author's name and version fields, these are all just metadata that are non-actionable. This is basically for human consumption, not for the machine to do things. So we're going to ignore those for right now, and we're only going to focus on channels and platforms. Channels basically defines for us what are, this is currently there's only one in here, it's just conda forge, but channels is a priority ordered list of conda channels, basically conda package indexes from which to actually search for the dependencies that we're going to ask for. So by default, Pixi uses conda forge, which is the public and open source and community maintained package index, but then there's also package indexes like Bioconda that might have tools for the bioinformatics community. And then there's also private indexes like proprietary but public package indexes like the NVIDIA package index, which until recently used to host all of NVIDIA's conda packages. There's also this platforms field, and this lists all the different computational platforms that we're going to try and actually solve these environments for. Here, we're solving for Linux 64 because I'm on an x86 based Linux machine, but we can also solve for platforms like Apple Silicon or Windows or x86 Windows, and we can solve multiple platforms simultaneously, but have all of them be resolved into a single lock file. So for excuse me, for clarity and to try and make it easier to avoid some noise, I'm going to delete the authors bit here just so that my screen is a little bit easier to follow. You don't have to do that. I'm just doing it for kind of simplicity. So we've now basically covered the most important bit about the workspace table. But now let's actually do something actionable by looking at the dependencies table. So the dependencies table is where we declaratively specify what are the actual tools or requirements or dependencies that we want in our computational environment. And we can do that. So this TOML file is just a text file. We could directly edit it with a text editor, or we can use Pixi's command line utilities itself to do this. So for example, if we say we want to add awkward as a dependency for our computational environment, we can do this simply by just typing Pixi add awkward. And it will think for a second, and we can see it solving, resolving, fetching information, and updating a lock file. And so now it tells us that it's added the latest release of awkward to our environment. So if we now try and check out what that actually means, if we list the contents of our repository, we see we have some new files. We see that we have a .pixi directory, and we also have a file called pixi.lock. Additionally, if we now look at the contents of our pixi.toml file, we now see that it's been updated to show us that there's a dependency called awkward now. And it by default gave us the latest version, version 2.8.9, and assumed that things are going to be semantically versioned, and so added an upper bound of 3. Pixi assumes that you're kind of working in an application-like setting, not a library-like setting, so it adds upper bounds. But these are not required. You can edit or adjust these things however you would like. Okay, so what actually happened though? We added a dependency, but what does this mean? If we use the Pixi info command, we can now see we'll get information about our system, different workspaces and things, but then we also see our environment. There's a default environment that's been created for us, and it currently has one dependency that's been defined for it, which is awkward. So we now have a computational environment that's already been made automatically for us. And if we ask for a Pixi list now, which will list what's actually in that computational environment, we see that we get a bunch of stuff. Since I'm zoomed in on my computer, this is a little bit difficult to read, but if I zoom out for a second and rerun this, then you can see that there's many different packages that have been installed, even though we only requested awkward, which is highlighted here. And we could also see just what we requested with Pixi list-x. Okay, but why are there all these different packages? So when we define in our pixi.toml file that we have a dependency on awkward, it not only gets the awkward package, but it gets all of the requirements for us to be able to use awkward as well, which also includes things like Python. So if we look at Python, then we also have defined and resolved a Python dependency so we now have Python 3.14 installed in this environment as well. And we can now actually use this computational environment with the Pixi run command. So if I type Pixi run Python, I haven't had to explicitly activate anything, but I'm dropped into this Python interpreter now, and I can do things like import awkward. And if I now look at where awkward is, then I can see that this actually lives in the site packages directory for this Python 3.14, which exists underneath this .pixi directory system that we have in our in this repository. But so we've been able to automatically use this environment without having to explicitly activate things. But if we wanted to have an interactive shell with this environment activated in a maybe more kind of like a conda like system, we can do that by using the Pixi shell command. And so we now see after a second, then we're dropped into a new subshell that with the prompt updated to kind of hint to us that we're in a new environment. If I now ask for what is the Python that's on my path, I see that this Python is the Python that comes from this default Pixi environment. And if I ask for the Python version, I see it's Python 3.14. And again, if I run Python, I can do import, if I can spell, awkward. And we can see that that awkward is the same awkward that we were looking at before. Okay, so that means that we've been able to, and this Pixi shell drops you into a subshell. So if I want to exit back to if I want to exit out of this environment and return to the state I was before, I just type exit, I exit my subshell, and I pop back up again to the level before. So that allowed us to create so we've been able to automatically create environments and add dependencies very easily. But now let's say that we want to define different computational environments or be able to add dependencies, but that we only want to use sometimes. We can use this, we can use the feature utility inside of Pixi to define something called a feature, which is a little confusingly named, which is essentially a Lego-like building block of a computational environment. It by itself is not an environment, but allows us to compose different features together into environments. As an example of this, if I type Pixi add feature lab, and then define things like notebook and Jupyter lab, then this will now add these dependencies to a new feature called lab. And if we look at our TOML file, we see that there's now a new subtable that is a feature table where we've defined another dependencies table that is now has notebook and lab installed in it. If we now want to create a new computational environment, we can do this by typing Pixi workspace environment add, and now we're gonna add, we're gonna bring in this feature that we just created called lab, and we're going to create a new environment called interactive. So it says added environment interactive, and if I now look at my TOML file again, then I now see that there's an environments table where we've defined a new environment called interactive that builds off of this lab feature. And if we want to, we notice at the moment that these dependencies are kind of left as star. So that means that they can be any version. If we wanted to make them explicit versions, we could do Pixi upgrade feature lab, and that will actually resolve them into their latest versions. So if we look at that again, we now see that these actually have lower bounds and upper bounds applied to them. Okay, so also this interactive environment, unless we explicitly tell Pixi to do something other than that, it will build upon our default environment. And so if we look at Pixi info again, we can now see that in the environments, we have two. We have default and interactive. But we see that the interactive environment builds from both the lab and the default feature. And so it has dependencies of Notebook, Jupyter Lab, and Awkward defined inside of it. So this now means that we can actually do things with inside of this computational environment. So if we run Pixi run -e for environment interactive. So if we define the environment we want to actually run this command in, and if I now run Jupyter Lab, then we see that it's resolving and installing things, and then it's going to pop up for me a new Jupyter Lab session here inside of the directory system. So I'm going to go ahead and shut that down though, and go back to the command line, because that's useful to be able to define that we want to be able to run different commands in different environments. But let's maybe make that easier to work with. So we can use, if we look at the pixi.toml, we see that there's this tasks table again. Let's now add a custom task that will allow us to actually run Jupyter Lab just with a more simple command. So I can do pixi task add, and we're gonna add this task, this action to the feature, to the lab feature. So this is going to be something that is composed within this Lego-like building environment. And then we can also give it a human readable description of, let's say, launch Jupyter Lab. And then we're going to also give it now the task a name. Let's call it lab again. And then we give it what the actual command is, which is to run Jupyter Lab. So if we now look at the toml table again, we now see that under the lab feature, there's now a task that is called lab and has a command defined for it. This kind of nested structure is the default structure. That's fine, but I find it a little bit ugly to read at times. So we can also go in and take advantage of the actual features of toml to add a sub table called lab. And now I can simply just take these fields that exist here and paste them in here. So I've now redefined the structure while keeping the commands the same. So I now have a task called lab that will run Jupyter Lab for me. So if I actually do that, if I do pixi run lab, then we see that it once again is now launching Jupyter Lab. And if I bring this back over, I see that I once again have a Jupyter Lab session running. And I'll shut that down once again for demonstration purposes. And you'll notice there that we didn't even have to define what computational environment we needed. This is because Pixi is able to look at the task system and see that there's only one environment in which this lab command is defined. It's defined in the interactive one, so it will automatically run it in there. Pixi also has a canonical feature of having every workspace having a start command, so that anytime you enter into a repository, you can simply run pixi run start if there's a Pixi project, and it will kind of dump you in or drop you into what is kind of the default interactive experience. We can do that as well. So we can now say, let's have running Jupyter Lab be that default experience. So let's do pixi task add feature lab. But instead of redefining that command again, let's instead tell Pixi to have this start command actually depend on the existing command we already have. So we can use depends on equals lab. So this is saying instead of executing something new, instead execute the lab command. And let's call this start and give it an empty string as basically the command. Again, I find the syntax by default a little bit ugly, but we can clear this up again by saying that this is start, and we can say depends on equals, and then we'll just have a list where we have it depend on the lab command. And if we now save this, I can now just do Pixi run start, and it will automatically launch me into Jupyter Lab, which is a pretty nice experience. And also, the great thing is that if someone doesn't have the environment installed already, Pixi will automatically install it for them and then run the command. And we can see that we're now in this interactive session where I have Awkward installed and is usable. Okay, so I'm going to shut this down for time. And let's now do one more thing before we kind of move on, because we only have about 10 minutes remaining or so. We also, in this repository, in this directory, have this lock file. And this is basically a structured file that contains information about every single dependency that's installed in this environment. If for time I look at the Mist website that I built around this, we can see that this lock file and this example lock file, which should match the one that we have, is actually a structured YAML file that has basically two sections, an environment section and a packages section. In the environment section, for every computational environment that you have installed, it will then basically list for all of the computational platforms all the locations on the internet where to actually go and get all the different packages that you have defined. And then in the packages section, it will then go and list all the metadata about that package, all of its dependencies, the file again, as well as its digests, like its SHA-256 and MD5 value. And it will also give information such as a timestamp of when this package was created, so that you can even do operations that depend on Unix time to try and restrict or modify the environment. So this log file, along with the Pixi manifest, this pixi.toml file, fully define the computational environment down to the digest level, which means that with these two files, as long as the package index that you got these tools from still exists, you are able to reproduce the environment byte for byte into the future. Okay, so quickly for time, so far, if we look at our platforms, mine shows Linux 64, but yours will show whatever operating system you are on. That might be OS X ARM 64 or Win 64. We can actually, in this single lock file, though, support multiple different computational environments. So if I now say Pixi workspace platform add Linux 64, OS X, ARM 64 for Apple Silicon, and Win 64 for x86 Windows, then when I add this, it will add all of those platforms to the platforms list, but then also resolve the environments for all of them as well. So now, if I look at my Pixi file, I'm supporting all of these platforms, but the computational environments I've defined have also been resolved for them as well. So I'm not on a Mac, but I've been able to in a single command now update that information. So as an example, if I do Pixi list platform OS X ARM 64 and look at awkward, it now tells me information about the packages for awkward that it has for the OS X ARM 64 distributions, which if we compare that to Linux 64, which is what I'm on, we can see that the versions are the same, but the actual builds are different. So all of this information is being stored inside of the lock file. So if I grep, for example, like awkward cpp pixi.lock, then we can also see that the lock file has information across all the different platforms for the actual builds of awkward CPP. Okay, we've been using conda packages so far, but let's say that we also want to be able to bring in tools that might only exist on a Python package index like PyPI. They don't exist on conda forge. Um, the PyHEP ecosystem in general has excellent support on both PyPI as well as CondaForge. So I'm just going to use an example that I know is on both, but we're going to just show it only existing. We're going to show it using getting it from PyPI. If I do Pixi add dash dash PyPI hist, then Pixi will now use libraries that come from the UV library to actually go call out to PyPI and be able to resolve the HISP package and get all of the Python packages that it needs for HIST. This is taking a little bit of time because it needs to resolve for everything. It's now done that, and if I look at my pixi.toml file, then at the bottom, I now see that I have a PyPI dependencies table that also defines hist. And if I now do pixi list hist, then I see that I now have this tool from PyPI instead of conda and it's also installed all of his dependencies like boost histogram and histoprint from PyPI as well. But all of these things live in a single lock file, so I've been able to now merge both conda packages and Python packages into a single computational environment. Okay, so we don't have a lot of time left, but to make this at least kind of useful for everyone as an example into the future, if we do git status right now, we see we have a few files. Let's do git add git star to get our git attribute files. Let's add the let's also add our git add pixi star to get both our pixi manifest and our pixi lock file. And let's create a commit here that just says add pixi environment. Okay, if I now push this up to my branch and create a new pull request, and if so, we're just going to, this is a single commit pull request. We're just going to go ahead and merge this into main. But this now means that anyone who has this repository can go ahead and now clone it. So if I, for example, clone this repository into somewhere new, so if I go to a new location on my computer, temp directory, and make door, let's do make dir PyHEP example and go into here. If I now do git clone of that repository and now cd into it and go to the example directory where there's this pixi toml and pixi lock file, I haven't done anything so far, but I can just now, we just cloned this repository fresh. I can simply just run, let me get this on screen, pixi run start, and it will now go ahead and install the full environment, which it did really quickly, and launch JupyterLab for us. So, and that will work for anyone who has any of the platforms that we described, like an Apple Silicon machine, an x86 Windows machine, or an x86 Linux machine. That will all just work automatically. We only have maybe 5 more minutes, so I'm going to kind of speed run through just the fact that we can also do we can do some things using Python projects as well. So if we go to the next section of this tutorial using Pixi with PyProject.toml based projects, I'm going to actually go to the repository for this this talk, and I'm going to clone this down to use some example files that I have inside of there. So let me do git clone of that repository. If I now go into this repository and go into the code section, then there is packaging. under the examples, and there's, okay, so if I'm inside of this kind of example directory that I've created before as kind of an example Python project with compiled C++ extensions. And so this is currently just a normal Python project. If you install it, you will get if you install it locally, you'll get this project with Python bindings with PyBind 11. If I now run Pixi init in this repository, though, it detects that a PyProject TOML file already exists, and it asks if we want to add a tool.pixi table, subtable to the configuration. If I say yes, then it's now added this. If I now look at the contents of pyproject.toml, at the bottom here, I now see the subtable, which is the same workspace structure that we know of before. And it also automatically defined a PyPI dependency for us of the name of the Python project. And it has this path equals dot, which is saying make this a local project and a local install. So if I now just simply type Pixi install at the command line, then this is going to do a few things. It's going to automatically add a Python dependency for us. It's then going to also it's going to install all the dependencies of the project from PyPI, and it will also locally install our project for us. So if I now do Pixi list, I can see that inside of this environment, I have this Rosen CPP example project that we made, but then we also got our dependencies of SciPy and NumPy from PyPI while getting things like the Python dependency from Conda Forge. So this now allows us to also be able to interact with our project. If I do import Rosen CPP, then I can see that I'm getting the same environment that I'm getting the project from the installed environment. So this is useful, but you might reasonably ask, okay, that's nice, but I can do this with UV as well and actually faster. And that is true. UV is able to do all this faster, but UV is a really great tool that's optimized for Python projects, but Pixi is able to use both Conda and Python projects. So for example, we can't use UV to install compilers that we might want our project to be able to use, but I can do Pixi add CXX compiler, and Pixi will now install a C++ and C compiler from Conda Forge that will be installed inside of our computational environment and will be used during the build of our Python project as well. So that now means that I'm able to just define build tools for multiple platforms that can be used across any computer, which means that I now have made my project built more reproducible in its build as well. So there are situations in which you want to be able to use UV to just build Python projects or install Python projects super, super fast. But there's also situations in which you want to be able to use Pixi to be able to have things be more reproducible and more robust. And also, let's say you might have much more complex dependencies that are large, like maybe boost or root that are coming into your project. With Pixi, you can get those tools from Conda Forge, where you might have to have a local Git submodule that you have to locally build if your project depends on them. If your project depends on them, if your Python project depends on them. For time, I'm going to skip basically the rest of showing how to also add testing environments. And I think I'll basically just finish by mentioning that a really powerful feature of Pixi is the fact that it also allows us to have reproducible hardware accelerated environments. All of NVIDIA's CUDA library stack is now distributed on Conda Forge. So that means that if I For example, if I go back up one more, yeah, so if I go and now make a project called, or initialize a project like CUDA example, and I go into CUDA example, I can use Pixi to define expectations that I have on the host system, the host machine, about what sort of resources it will have. So I can ask for things like Pixi workspace, system requirements, add CUDA 12. And this now has created the expectation that the machine that this environment lands on is going to have an NVIDIA driver that supports at least CUDA 12 on it. It's not going to explicitly enforce this, but it will make sure that dependencies that rely on versions of CUDA 12 or greater are properly resolved. What's really great about this means that I can now do things like Pixi add PyTorch GPU, and this will now go and from Conda Forge get not only the CUDA enabled version of PyTorch, but it will also get all of its CUDA dependencies as well. And so if I now do things like Pixi run Python, I can now do import torch, and I can see that torch.cuda is available. If I spelled it correctly, returns true. So I've been able to now define a hardware accelerated version of PyTorch, and also if I look, if I do Pixi list CUDA, I can also see that my environment fully defines multiple different, all the CUDA dependencies as well. You're able to do this and define this viable CUDA workspace, even if you don't have CUDA, an NVIDIA GPU on your machine. So you're able to define viable workspaces for hardware accelerated workflows, even if you don't have those resources on your machine, but you know that a target machine might. And that's a really powerful feature. All right, I think I'm sufficiently over time at this point, so I'm going to stop here. I'm happy to answer any questions people might have either now or in Zulip in chat later. And then on the MIST website, there's additional resources and GitHub repositories for people to check more things out later.